Mastering data virtualization. Data virtualization success hinges on one person, the architect, who is responsible for ensuring that data virtualization effectively supports data caching and results caching, and what are the key strategies they employ to achieve this. In a data virtualization environment, the primary responsibility for ensuring effective data caching and results caching lies with the data virtualization architect or the data virtualization administrator. This individual plays a crucial role in designing and implementing an optimal caching strategy that leverages the capabilities of data virtualization to improve data access performance, reduce latency, and decrease the load on underlying data sources. To achieve effective data caching and results caching, the data virtualization architect or administrator employs several key strategies. First and foremost, they must have a comprehensive understanding of the data virtualization platform's caching capabilities and limitations. This includes knowledge of the different caching mechanisms available, such as in-memory caching, disk-based caching, and distributed caching, as well as the rules and configuration options for each. Next, the data virtualization architect or administrator must conduct a thorough analysis of the data access patterns and usage behaviors of the various applications and users that interact with the data virtualization layer. This includes identifying frequently accessed data, peak usage periods, and the types of queries and analytical workloads that are typically executed. This analysis enables the identification of the most beneficial caching opportunities and helps to prioritize caching efforts. The data virtualization architect or administrator must also collaborate closely with data source administrators and application developers to identify the optimal caching strategies for each data source and application. This includes discussing data freshness requirements, data volatility, and data retention policies to ensure that caching is implemented in a way that balances performance needs with data freshness and integrity requirements. In terms of specific caching strategies, the data virtualization architect or administrator may employ several techniques to achieve optimal caching. These include 1. Cache hierarchy, implementing a hierarchical caching mechanism that includes multiple levels of caching, such as in-memory caching, disk-based caching, and distributed caching. This allows for efficient caching of frequently accessed data and minimizes the number of requests that need to be routed to the underlying data sources. 2. Cache invalidation, implementing cache invalidation policies to ensure that cache data is refreshed or updated when the underlying data sources change. This can be achieved through the use of time-based caching, event-based caching, or incremental caching. 3. Cache preloading, preloading the cache with frequently accessed data or critical datasets to minimize the initial latency and improve overall performance. 4. Cache clustering, implementing a distributed caching mechanism that spans multiple nodes or servers to improve caching performance, scalability, and fault tolerance. 5. Data aggregation and summarization, implementing data aggregation and summarization techniques to reduce the volume of data that needs to be cached and to improve query performance. 6. Cache optimization, continuously monitoring and optimizing cache performance using analytics and monitoring tools to identify areas for improvement and opportunities for optimization. In summary, the data virtualization architect or administrator plays a critical role in ensuring that data virtualization effectively supports data caching and results caching. By understanding the data virtualization platform's caching capabilities, analyzing data access patterns, collaborating with stakeholders, and employing optimal caching strategies, the data virtualization architect or administrator can achieve significant improvements in data access performance, reduce latency, and decrease the load on underlying data sources.